Hello everybody. Today, the week number 4, our topic is neural networks, and this is a quick review of neural networks. I've been talking about neural networks. I've been discussing neural networks with you for the whole week, and this is like a short version of my presentation. Unfortunately, I'm not going to show you like, the built-in videos that I prepared for the actual webinar, but I'll leave the links in the description below the video so that you could check these videos out and I hope, get inspired by neural networks as much as I am inspired now. So, without further ado, let's talk about neural networks. We'll start by talking about brain cells first, as the source of inspiration for IT developers and scientists to build a software neural network, an analog neural network that works and functions kind of the way brain cells do in our brains, in our heads. So a brain cell, most commonly known as neuron, is consists of three parts. We have the cell body, the main part, that can be considered a processing unit. We have dendrites that connect this neuron to other neurons to other cells, and you can consider them as input parts, the inputs of the cell. And we have a single output that is an axon that connects this very cell to other neurons, to other dendrites, and so on and so forth. So the number of these cells in our body, in our brain, is really huge. Some scientists say that there are 500 billion cells like this. Others estimate that to be even larger. But we are not so sure because the process of research is slowed down because most of our research procedures are invasive, and we don't want people to die while you study their brain, because that also leads to the neurons stop functioning. And if you want to look at the way these neurons, these cells, function, you need a living brain and you need non-invasive means of research, and they're not so precise and they're not so fruitful as the invasive ones. So this is how the brain cell looks like. This is a rough diagram. This is not the exact thing. And you need to understand they're really tiny, and there are dozens of connections and thousands and thousands of them in each of the cluster inside a small square millimeter tiny part of your brain. So roughly speaking, you can say that there are a couple of common things between a brain cell like this and a microchip that consists of transistors that have single inputs and single outputs, and they have two. But the difference is that transistors in our computers operate on two states: the 0 and 1, the low and the high. And by using logic gates and different logic constructions, we can emulate the work of a neuron. And that's what people do, what researchers do in terms of IT when they create a neural network. Neural network is basically a software emulation of this neural network inside our brains, in terms of the multiple inputs and the processing unit and a single or multiple outputs. So you can represent any neural network as a graph with multiple nodes and multiple connections. As you can see in this picture, we have a layer of input units in red and a layer of output units that are in yellow, and multiple or several layers of hidden units that are in between. and there are numerous connections between them, as you can see. This is how a standard feed-forward network looks like. It's called feed-forward because you send inputs to the input nodes or the input units, and then the signal kind of is propagated forward through multiple layers, and it gets stronger, it gets weaker, and then you get the output. So this is a feed-forward network. And the way a certain signal moves through this network depends on two things. The weights that are the condition of each of the connection, and the biases or thresholds that are the parameters of each of the hidden or inner node. So as soon as the signal goes through through a connection, a weight is applied, for example, in multiplication. So, for example, this connection here has a weight of 0.2. So signal 1 is multiplied by 0.2. So this node here, number 2, this hidden node, receives the signal 0.2. But then it receives a couple of other signals also multiplied by their weights, and it sums them up. So, for example, the sum can be like 1.6 in total for these three connections, for these three signals, and then it can compare the sum of the inputs with that it received with weights with the threshold. If the threshold is lower, then the signal gets propagated forward. If the threshold is higher, if the bias is higher, then this node sends 0 signals further on, and the signal is not propagated. So the second feature of any neural network is its ability to learn, or like speaking in more detail, adjusting its behavior so that the output, the result of its calculation, gets closer and closer to what you want from the network. So basically, this is done through this process called backprop or backpropagation, when you compare the result that the network gives you with the result that you actually wanted, and then you adjust the weights and the biases, like moving backwards from the output units to the hidden layers, so that the next iteration of the network's work will be closer to the result that you expect from the network. So now, well, there was an example of this network, in this example, in this particular example, you could watch that later. A generation of 25 neural networks like this were created, and they competed against each other in the way they can beat the world 1-1 in Super Mario. And they got better and better with each generation, because in this process that resembled evolution or natural selection to some point, so that they got really, really better. This is a very nice and interesting video. You should check it out. So, but now we will talk about the perceptrons. This is a neuron of the first version that came to the researcher's mind, and that's basically what I already told you about. So inside every node in the hidden layer and the output layer, there is this activation function that compares the sum of the inputs that it received with well, the threshold or the bias. If the bias is larger, then 0 is sent or propagated further. If the bias is lower than the sum of the inputs, so it receives some strong signals from all these three connections, it will propagate 1 further on, because it's larger. The sum of the inputs, the sum of the weights is larger than what it has as an activation function, as a threshold. So that's how this basically works. But the downside of this perceptron neurons is that it sends just zeros or ones, and these are pretty rough numbers in terms of learning. And for example, in this very network, if I change just through backpropagation, I change just one weight or I change one bias, it will lead to the whole to this whole system to behave in a completely different way, so that it doesn't learn like steadily, doesn't learn like by confirming the positive results and neglecting the negative results. It learns by like randomly adjusting its behavior, and when it fits, it fits. If it doesn't fit, well, it tries to do something else. So this is a very rigid, I would say it's a very rigid system, because it only works on zeros and ones and some weights that multiply zeros and ones to each other. So that's why probably researchers and IT developers decided to use a different type of neuron based on not on just activation function, as you can see here, but on the sigmoid function inside, and they called it sigmoid neurons. And you are probably familiar with the sigmoid function. This is the representation of the sigmoid function. So that the result of the calculation, the sigmoid, depends on the sum of the inputs and the bias z here. And well, as you can see, in the extreme cases, like if the sum of the inputs is really negative, -10, or it's really positive, like +7.5, the result of the calculation of the sigmoid function is still like close to 0 or close to 1. So in extreme cases, when you tell the network that it shouldn't do that, it will not. Or if you say that this is a very effective thing that you just did, it will support this idea, just sending 1 to the next node. But in the in-between cases, like if z is really close to 0, if z is like a couple of decimal numbers away from 0, you see that the output is differs in a very large scale, from 0.8 to 0.2, and the trick is that this is a continuous value between 0, the result is always a continuous number between 0 and 1, so that it resembles a natural kind of learning process in a better way. It resembles the way people learn and the way you adjust your behavior by learning while learning. Because if you, for example, learning how to play baseball, if you're learning how to play bowling, and you just threw your first ball into the pit, you will see that you missed a couple of centimeters or meters away from the goal, and you will adjust your behavior slightly, not just completely change your behavior. So this sigmoid function represents that, and this sigmoid activation routine represents this more smoother way of learning in this in-between cases, when the z, or the sum of the weights and the bias, is close to 0. So well, now it's time for us to move to the actual implementation and see how these neural networks are built, how they're made while using Python as one of the most suitable languages for this kind of job. So first we build a network by creating a synapses matrix. There is a built-in function called numpy or numpy function, and these two lines of code basically create the synapses matrix. Then we actually built the network. As you can see, it has like 60,000 units and 3 layers. Layer 0, or the first layer, is just the input layer. You set it up. Then we create the first layer, and we say that the first layer, the middle layer, is a sigmoid function of the inputs and multiplied by the synapses for this layer, for the 0 layer. Then we have layer 2, this is the output layer, and that's a sigmoid of the multiplication of the previous layer result and the synapses for the second synapses. So that's how you build this network. This is the creation process. Now let's see how this network can learn, how we can create the learning procedure or learning process of this network. The learning is based on the so-called cost function. Of course, the cost, when they say cost, they mean the difference between what you wanted from, what you expected from the network and the result that the network gave you. So you could actually calculate the cost by subtracting one from another, y minus a. But the scientists and the researchers decided to use a more sophisticated cost function, for example, a cost function like this, when we have C, cost function of weights and biases that equals, and it depends on the number of inputs, it depends on the input that you gave to the network, the output that you expected, y, and the output that the network gave you. And as you can see, this is a quadratic function, and all these deltas and gradient descent functions and quadratic functions are used so that in order to smoothen things up, to make them resemble an actual real learning process more, so that the behavior of the network and the backpropagation will be more fruitful, will be less random. So let's see how it's done in our example of a Python-based neural network. First, we calculate the error of the output. You remember that layer 2 is the output layer. We check how far the prediction is from the real value. Here we subtract L2 from Y, and then we receive this L2 error value. And we use this L2 error value in the formula where we calculate delta for layer 2. So delta represents the amount by which you should change the synapses of the second layer. That's L2 delta. And you multiply the L2 error by the sigmoid value of the output and the derivative. So that's how you do that. And then we need to calculate the error for the hidden layer, the in-between layer, between the input and output. And this is the formula for that. We need to understand how much this hidden layer, L1, layer 1, contributed to the error in the output layer, layer 2. And so basically multiply the layer 2 delta with the synapses 1 transpose. And then we use this L1 error value for the same kind of formula we had here, but for the not for the L2 delta, but for the layer 1 delta, so the middle layer delta. We use the same function here. So now as we calculated both deltas for the middle layer, the hidden layer, and the output layer, we can do the backpropagation and adjust the synapses matrix here with both L1 and L2 delta at the same time. So that's how it's done. Roughly speaking, this is one of the examples of how you can build a neural network, and I'd like to inspire you. I wanted, with this presentation, I just wanted to inspire you to pay attention to this new and promising field of information technologies, and you could watch a couple of other videos with implementations from projects like OpenAI or TensorFlow by Google. I would like to encourage you to read about this more or to watch some videos. I will leave the links in the description so that you would get inspired and probably you would get interested in this topic, and maybe some of you will even dedicate their lives on developing neural networks or teaching neural networks how to get better at what they are doing. So there are a couple of examples, you could watch them later on. For now, thank you very much for your attention. See you next week, and if you have any questions, please ask me in the comments or in direct messages in contact. See you. Goodbye.